In this video, we are going to do an example of a proof of something in number theory, and I'm going to introduce to you the concept of writing proofs in color and explain why I'm doing that and what the purpose of each color is. This is the thing I'm going to be asking you to do on every single homework assignment and on your exams as well. The lemma that we'll be proving today is something that became apparent to us in our previous videos. It's a key fact that's important to prove that the Euclidean algorithm works as a mechanism for finding the greatest common divisor of two integers. And the lemma is as follows. We're going to remember that we have two positive integers, a and b. We're going to write a according to the quotient remainder theorem as a multiple of b plus some sort of remainder. And the lemma that we're going to prove is that the GCD of the integers a and b is equal to the GCD of the integers b and r. And this is really important in establishing that when we're using the Euclidean algorithm moving from one stage to the next stage, that we're preserving the GCD when we move from stage to stage. So that's the lemma that we're going to be proving. I want to make a little bit of an aside about mathematical words and what they mean. I remember for a long time not knowing what a lemma was, and so I want to make sure that anyone who's watching knows what it means to be a lemma. And it's somewhat loosely defined, which is part of the reason I had difficulty with it. What a lemma is some sort of mathematical statement that requires proof, but by itself maybe isn't horrendously useful, or the proof might be kind of small or easy. One of those couple of things. So something about it is a little bit less, either the proof or the use of the fact. And very frequently, what lemmas are things that you prove so that a theorem can reference the lemma later on and not have to take up that space in the theorem to prove this particular fact. So that's what's going on here. The big proof that we're looking at, the theorem that we're looking for, that we won't actually prove in this class, but is proven in mathematical literature, is that the Euclidean algorithm is a process that works to obtain the GCD of two integers. Part of what we need in order to prove that theorem is a proof of this fact. So this is kind of like a supporting material for a bigger thing, and that bigger thing would be called a theorem. Something that's not written down in here is a corollary. Some people say corollary, but a corollary is a statement that normally would come after a theorem, which would be a special case of that theorem. That's kind of like a lemma, but as opposed to being used before the theorem, it comes after the theorem. So that would be a corollary. Of theorems, there can be theorems of various levels of importance. If you have a theorem and it just says theorem and you don't have any other way to reference it, that's important. It's more important than a lemma. But a theorem that has a special name is a more important theorem than other kinds of theorems. So an example of that might be the sandwich theorem from calculus, or Lagrange's theorem. Particularly when it's named after a person, you know you've got something important there. And last but not least is something we have seen an example of already. If you're looking at a theorem and it is called the fundamental theorem of, that is the be-all, end-all of theorems. It's super important, and you better have it memorized. So that's just a little bit of a hierarchy of the way that things are named in mathematics, which I found confusing when I was learning. Now, let's start talking about proof in color, what the colors are going to be, and what my philosophy is here. So I came across a quote by a person that I would call a mathematician, Bonnie Jo Campbell, but she's also a writer. I think most of her time currently is spent writing. She's alive, which is an interesting thing. Most of the math we're studying is from the 1800s, and so most of the people we'll learn about in abstract algebra are very dead. So it's nice to hear perspective from somebody who's alive. And she was talking, I think, about the differences between math and writing. And she said a mathematical proof is a beautiful thing, which lots of mathematicians will say. But when you're finished with it, it's just really only about one thing. A story can be about many things. And to me, that encompasses what I'm trying to capture with the way we run this course this semester. I want us to write proofs, and I want our proofs to be beautiful. We're learning proofwriting, but this is an upper-level mathematics course. We're trying to learn not just to get through a proof, but make it into a thing of beauty. And I think the colors will actually help us with that, not just because they're physically pretty, but because they will help us make the writing elegant, and that can make a mathematical proof pretty. The story aspect is really what I'm trying to get into with this course log. The course log is a place for us to collect the story of abstract algebra, because honestly, it's a really good one. And I know my opinion is biased, but there are lots of interesting sides and stories and things that come about in the pursuit of the subject of abstract algebra. And as we learn that and discover that, I want us to celebrate it. And so that's what the course log is going to be. The many various types of stories of abstract algebra, not just proofwriting, proofwriting, proofwriting. Concerning the colors, we are going to have a system. As you're learning to write mathematical proofs, you start out maybe with a discrete structures course, or maybe just as you're solving any particular proof, and you're just trying to stumble your way through it. You don't really know what you're doing yet, you're just learning, you don't really see the path yet that the proof is going to take, and so your initial pass at proofwriting, either for a specific proof or proofwriting overall, is going to be really rough. But the more you go over that particular proof or that kind of proof, or you practice proofwriting, you refine your skills a little bit. And ultimately, what you turn in should look a little bit more like the tail end of this horse. You should have practiced it and gone through it until you've really ironed out all the kinks and you have something to display that's very nicely done. So this should be the process of your proofwriting skills, just on a small scale, on a particular problem, and also throughout the class, hopefully, as we practice our proofwriting skills. So keep in mind when you're turning in a proof, I don't want to see your first attempts at figuring things out. I want you to revise and revisit and reflect on that learning process until you feel like you can put it into words at this caliber. To help us with that, I'm going to use a technique that many lawyers do when they're preparing notes to go into trial, which is they color code them. So everything they're writing down to go into trial has a color associated with it, so they know not only what they want to say, but why they're saying it. Why is this relevant? Am I citing a previous case? Am I trying to draw the jury to this particular conclusion? There's a whole color coding scheme that lawyers use as to why they're making the points that they're making. And I think if we apply a same thing to proofwriting, I'm going to write this sentence down in a proof. Why am I writing it down? What is so important about this particular sentence? If we have these colors and we apply that reflective process to our writing is going to get a whole lot better. So in the next set of videos, I am going to go through the example lemma that I showed to you at the beginning, and I'll be using this color coding scheme. Anything that is an assumption to me, it's something that I start with, and so I'm going to make it green, like a green light. Any conclusions that I draw, those are kind of stopping points. When I get to the end of the proof, I should know I'm at the end, and so that should be red, although there are times that I draw conclusions earlier in the proof, so I could see red there as well. But in essence, it's something of a stopping point. We should need to reach out of our assumptions occasionally to quote lemmas and theorems, much like a theorem would appeal to the lemma that we'll be proving here. And when we do make appeals to definitions or theorems, let's put those things in blue. It's a math class. Sometimes we're going to do computations to get from point A to point B, and we'll put those things in purple. And every now and again, there are things that we do in a proof just for good writing's sake that aren't necessarily any one of these things. So we're going to kind of use black as an else here. Every now and again, you might just want to pause and tell your reader, okay, next we're going to do this thing, or first we're going to do that thing. Those directional types of statements are really useful, and so anything that doesn't fit nicely into one of these four colors will make black. And if anything else comes up, a technique that I've overlooked as we're writing our proofs, we can add more colors as we go.